Welcome to Lecture 3C, and today we're probably going to be covering a topic that you may not be familiar with, which is solubility equilibrium. So we're going to start off talking about insoluble salts. Precipitation is probably one of the most important types of reactions, both industry, medicine, geology. There are several fields where precipitation becomes important. Here we're dealing with solid chemicals. So things like kidney stones, where you don't want them to be insoluble. Tooth enamel, again, something that we don't want to be soluble. And geologic formations, where we concern ourselves with the disappearance of them due to solubility under certain conditions. And in earlier chapters, we had talked about how certain combinations of anions and cations come together and form insoluble salts. Well, the term insoluble is somewhat relative because everything is always slightly soluble. It's just a matter of how insoluble it is. But nothing is ever absolutely insoluble. So even the things that are extremely insoluble or very, very slightly soluble dissolve a little bit and reach an equilibrium in solution. So today we're going to look at the mathematical relationships we have with these slightly soluble salts. So one of the more stereotypical compounds that we look at when we're studying solubility equilibria is silver chloride, and you can get it by the reaction of silver and chloride ions. They form the salt silver chloride. Now, if we were to take a sample of silver chloride, say just take a scoop of it out of a bottle and put it into water, for the most part, you're just going to see the solids sitting on the bottom. But at the ionic level or the molecular level, however you want to look at that, what you would actually see in solution are some silver ions and chloride ions floating around in solution. So they do form an aqueous solution, although it's extremely dilute. Now notice that we do have set up an equilibrium here. So this is an equilibrium reaction. Because it's an equilibrium reaction, we can set up an equilibrium expression. So we have an equilibrium expression here, Ksp, we'll talk about the Sp in just a moment, is equal to, because it's an equilibrium, it's still products over reactants. So we have concentration of Ag plus times concentration of Cl minus in solution divided by concentration of the silver chloride solid. Now, notice that we do have that Sp. It is the large K, so it is still an equilibrium constant. So all the rules we had for equilibrium constants prior all still hold. The Sp is just a label. It tells us it's a solubility product, and it just gives us a very specific condition under which this equilibrium constant is used. Now, we do see that AgCl, silver chloride, is a solid here. Now, because it's a solid, just like before, we do not include solids in our equilibrium constant expressions. The concentrations of those solids are constant, and they get worked back into the value of the Ksp. So what we end up with, the true equilibrium expression for the Ksp, is just nothing more than Ksp is equal to concentration of silver plus times concentration of silver minus. Now notice that our silver and our chloride have no exponents here, and that is because we have an exponent of 1, coefficient of 1 and a coefficient of 1. So that's why our exponents are unwritten as 1 and 1. As we'll see in just a few slides, if we have coefficients here due to the stoichiometry of different ions, when something dissolves, those coefficients do become exponents in our equilibrium constant expression. If we look at some values of certain compounds and their KSPs, you can see some of them are fairly large, 10 to the minus 5, 10 to the minus 5. Some of them are extremely small. The range of KSP values, equilibrium values, are just widely varied. We have 10 to the minus 5 all the way up to 10 to the minus 36. We have 10 to the minus 29 over here, 10 to the minus 11, 17, 19. So there's really quite a range in equilibrium constants for solubility. A lot of this is due to a variation in solubility as well as a variation in the stoichiometry of how things dissolve. So I mentioned before, we have the same rules for writing equilibria as before. Reactants are not included because those are the solids. So we always write our equilibrium reactions for solubility as our solid going to our ionic compounds. So here's something like magnesium fluoride, MgF2, It's going to break up into magnesium ions and fluoride ions, not an F2 ion, but two fluoride ions. Okay, so we write our KSPs, we include only the products, and we have our concentration of magnesium times concentration of fluoride ions squared. And our fluoride ion is squared because there are two of them in the equilibrium reaction. For something like a silver carbonate, we get two silvers and a carbonate ion. Notice we have a polyatomic ion here, CO3. The CO does not break its bond in aqueous solution. It's too strong for that. And so be sure you're familiar with your polyatomic ions. And so we have a very similar KSP expression here. We have the concentration of Ag plus squared. Again, the silver is squared because of the two here, and then times the concentration of the carbonate ion. If both have coefficients in front of them, then we just have a couple of different exponents. This is for calcium phosphate, Ca3PO42. We have 3 calcium ions, 2 phosphate ions, again, a polyatomic ion, very common with a lot of our compounds for KSP problems. And so here we have the concentration of calcium 2 plus is cubed, again, because of the 3 here in front of the calcium. And we have the concentration of a phosphate ion squared because we have the 2 in front of our phosphate here. Now, when we were using equilibrium values or equilibrium constants for acids, so your Ka and your Kb, you could just look at the value of that Ka and generally see how acidic something was. If it had a larger Ka value, then it was more acidic. A smaller Ka value said it was less acidic. KSP is similar, but not quite the same. You can't always do that, and I'll show you the reason here. So your KSP value does give an indication of solubility, but you can't use that as the sole determiner of is something more soluble than something else. When we are looking at Kas and Kbs, you pretty much always had a one-to-one stoichiometry between the hydrogen ion and the counter ion. Well, here in our KSPs, we have a very wide variety in exponents between different compounds, and that can really impact the value of the KSP. Even for things with similar solubilities, if they have a different stoichiometry when they dissolve, their KSP values become very different. And so what we have to look at is it something a little bit different? So we can use the KSP to compare the solubility of two compounds directly if they have the exact same cation to anion ratio. So if it's a 1-to-1 or a 2-to-1 or a 1-to-2, then we can compare the KSPs directly. And if it has a larger KSP, then it's more soluble. If they have a different cation to anion ratio than each other, then we have to go one step farther. And what we've got to do is use an icebox for the solubility, find the value of X, and the value of X will tell us the molar solubility of that compound. And we can compare the molar solubility between two compounds to tell us which one is going to be more soluble. And what molar solubility is the number of moles of that substance that is dissolved in 1 liter of a saturated solution. So it tells us exactly how much we can expect of that compound to dissolve in 1 liter of a solution. So just as an example, here we have two compounds, magnesium hydroxide and iron carbonate. We can see that they have a slightly different cation-anion ratio. Our magnesium hydroxide is 1 magnesium to 2 hydroxides. Our iron carbonate is 1 iron to 1 carbonate ion. We see that the iron carbonate has a larger KSP. So if we were to do a direct comparison would say that the iron carbonate is more soluble, but it is not. Okay? And that's because we cannot do a direct comparison because of the different ratio here. When we calculate the solubility, if we were to do an icebox on these, and we'll do one here in just a moment, we see that the solubility of magnesium hydroxide is just slightly bigger. Actually, it's about 10 times bigger than iron carbonate. So the lesson here is if they have a different stoichiometric ratio, you cannot compare them. All right, let's look at an example of how we calculate molar solubility. So we want to know what's the molar solubility of calcium fluoride, CaF2. It has a KSP of 4.9 times 10 to the minus 11. If we write out the equilibrium reaction here, we have calcium fluoride solid going to calcium ion, aqueous, and 2 fluoride minuses, also aqueous. We can set up an ice box here. For our solid, we always have more solid than we need before it saturates the solution, so we just say lots. It doesn't matter how much we have in here because it's not part of our calculation. Before the solid dissolves, we have no calcium and we have no fluoride. Now, the solid is going to lose some X amount. It's not really important what that X is for the solid, so minus X. Now, I'm going to gain X amount of the calcium because it has a 1-to-1 ratio between the stoichiometry of the solid and the calcium ion. So if I lose X of calcium fluoride, I'm going to gain X of the calcium, and I'm going to gain 2X of the fluoride, and it's 2X because I have 2 fluorides for every 1 calcium fluoride that dissolves. Very important that you keep that coefficient in there. So minus X plus 2X. When I add all these up, lots minus X is really tiny. I still have lots of solid left. I don't care how much solid is in there. I'm going to have X amount of the calcium because it's just 0 plus X. And my fluoride is going to be 0 plus 2X, so I have 2X for my fluoride concentration. Now my KSP expression, I'm going to have the KSP, which we learned was equal to 4.9 times 10 minus 11. That's going to be equal to the calcium ion concentration times the fluoride ion concentration squared. Only the fluoride ion concentration there is squared. So we can plug in our values. We have 4.9 times 10 minus 11 is equal to X times the quantity 2X squared. Okay, 2X squared. Now, when we get that, we have our KSP is equal to 4X cubed. Where does the 4X cubed come from? When I square 2X, I get 4X squared. 4X squared times X gives me 4X cubed. Very important that you do not forget to square that 2. Or if it were a cubed, we've got to make sure that we cube that 2. It's one of the more common mistakes that we make. Now we can solve for this. We divide by 4, we take the cube root, and we get an X value of 2.3 times 10 to the minus 4 moles per liter. This is our value of X, so that will be the concentration of calcium in the solution. 2 times this value would be the concentration of the fluoride ion in that solution, and it is all equal to the molar solubility. So X is the molar solubility here, 2.3 times 10 to the minus 4 moles per liter. Let's go the other way. We know the molar solubility of silver sulfate is 1.5 times 10 to the minus 2. What is the KSP of the salt? Well, if we write out the equilibrium reaction, we have silver sulfate, Ag2SO4, that's equal to, goes to 2 Ag pluses, plus the sulfate ion, SO4, 2 minus. So we see from the stoichiometry that we get 2 moles of silver and 1 mole of sulfate ion for each of the silver sulfate dissolved, for each mole of silver sulfate dissolved. So in my saturated solution, my concentration of silver is going to be 1.5 times 10 to the minus 2 moles per liter for the molar solubility times 1 mole of silver plus over 1 mole of silver sulfate. And this is really my moles of silver sulfate. So my moles of silver sulfate here would cancel, and I'm left with 3.02 times 10 to the minus 2 molarity of silver. For my sulfate, it has a 1-to-1, so I have 1.5 times 10 to the minus 2. My molar solubility for the compound, for every 1 mole of the compound, I get 1 mole of the sulfate, and I get the concentration of the sulfate ion of 1.5 times 10 to the minus 2. I can take these values, so here's my reaction again. I can write my KSP. It's going to be the concentration of silver squared. Again, that squared is because I have a 2 here for the silver. And the concentration of my sulfate ion here just has 1 because there's a 1 there. So I plug in my value for the silver ion concentration that we just calculated, 3 times 10 to the minus 2. That gets squared times sulfate concentration, 1.5 times 10 to the minus 2. And we get a KSP of 1.4 times 10 to the minus 5.